Okay, good morning, everyone. So today we have a talk from Augusto Berndt. Augusto kindly accepted our invitation to give this talk. Augusto has received his computer engineering degree from the University of Rio Grande, in Rio Grande do Sul State in 2018. And in 2020, he received the master's degree in microelectronics from Federal University of Rio Grande do Sul in Porto Alegre. And this year, he concluded the PhD in computer science here at UFSC. His work was supervised by Professor Christina Meinhardt. His research interests are EDA tools in general and application of machine learning to EDA tools. And currently, he lives in Berlin, Germany, where he is working remotely for the OpenROAD project. The OpenROAD project, which is managed, let's say, by a company called Precision Innovations. Okay, thank you for accepting our invitation, Augusto, and the floor is yours.
Okay, thank you, Ginso. So, good morning, everyone. I'm Augusto, as Ginso said. I passed by UFSC for my PhD, right? As you said also. And I'm currently working for Precision Innovations Inc., PII, as we call it, which manages the OpenROAD project. And today I'm going to talk about the RePlace algorithm, which is used as the global placement in OpenROAD, right? So this presentation, I made it internally for our company, just to show how the tool works. And I mentioned to Christina and Ginso that I could maybe extend this presentation and show it to students here. So yeah, let's do it. Okay, so this is an outline of what I'm going to talk about. I'm going to initiate by talking about the OpenROAD project and its difference from Precision Innovations Inc. Then I'm going to talk about RePlace, or GPL, as we also call it, from Global Placement, GPL. I'm going to try to explain how instances are moved inside of the algorithm, the electrostatic placement, and the gradient vectors involved. GPL also has special modes for routability and time-driven modes. Some challenges and contributions to the tool, and some conclusions with suggestions if people want to get started with OpenROAD. All right, so Precision Innovations PII is a company. It's a private company, and it supports. It provides support to its clients based on the OpenROAD tool, which is open source. Okay, so Precision Innovations does not own OpenROAD. They are two separated organizations. And PII is private, and OpenROAD is public and open source. So the OpenROAD project started by 2018, funded by DARPA, which is a government agency from the USA, and also by the University of San Diego. The University of San Diego is still involved today with the project. But DARPA is not anymore. It doesn't fund the project anymore, and so that's when it comes PII as a private company and keeps the project alive. So the OpenROAD project is open source. Anyone is free to use it and edit it freely as they wish to, including the source code. So I'd like to state here this is perfect situation for students and academic research overall. So if you want to make some research on EDA, you can use the tool. You're free to do whatever you want with it, differently from other private tools, which you cannot, for example, edit the source code. You have a lot less freedom to do things overall with the tool. So that's a good thing about the OpenROAD, which gets in front of the others, in my opinion, from the view of a student, right, or a researcher. All right, so I used the OpenROAD tool for my PhD thesis in UFSC, right? And there we used the OpenROAD tool and graph neural networks to predict the routing congestion of designs. And we used input data as only from logic synthesis without any physical information. And yeah, I used the OpenROAD tool to create all of our database with designs. And here are some images of the predictions and the targets that we achieved. Yeah, and the OpenROAD tool was really useful for that. Right, here I separated some links. I hope I'm able to share the slides with you guys, but the first link here is the OpenROAD project as a whole in GitHub. It's this link. And we also have two main repositories for the OpenROAD. We have the flow. We call it OpenROAD flow scripts. It's mostly uses Tcl language, and it's mostly used by designers. So this is the link to the repository here in the middle. And we also have the top level application of the OpenROAD. It's like the tool itself, which is mostly implemented in C++. And this one is should be more used if you are an EDA developer, if you want to make changes to algorithms inside of the flow itself. You should use this last one. But if you just want to play around with the flow, maybe generate a GDS2, you should use the one in the middle, which is the flow as a whole, right? And it uses the guides, let's say, the tool to produce the designs, right? Okay, so yeah, I separated the slide here with this flow in the right. I hope you guys are familiar with some of these names here. We have logic synthesis, floor planning, placement, CTS, routing. So these are the main steps in the design flow of circuits, right? And yeah, this image on the top here is all of the source code from inside of OpenROAD. So we have a directory with multiple tools. And what I wanted to show you guys here is that each step is implemented based on an academic approach. So when OpenROAD was designed, was implemented, was invented, people gathered a lot of different academic works, which solves independent problems along the flow, right? And they put it all together and made a tool able to go from RTL to GDS2 to make the complete flow, and using academic tools, academic implementations. So yeah, it's really nice. So each step here will have its own tool inside of OpenROAD. For example, logic synthesis, we use Yosys, which is an independent project outside of OpenROAD, but we use it. It's also open source. We have, for example, the floor planning. We use a bunch of different tools here. MPL, PAD, and PDN, for example, are three of the tools that work inside of floor plan. And placement, we have the GPL, which stands for global placement, right? And inside of placement, we also have the detail placement, DPL, which comes afterwards with legalization. And yeah, also a lot of other academic implementations, which went inside of the OpenROAD tool. All right, so yeah, RePlace and GPL. So yeah, I used RePlace on the title of my presentation, right? But I'm talking about GPL, as you may notice. So GPL is like an extension from the RePlace implementation. So RePlace itself was a succession of various works, all of them academic. And afterwards, the RePlace was brought into the OpenROAD and it became actually GPL, right? So yeah, it's an extension of an academic work. GPL stands for global placement. I left a link here with the README. In the README, you can see the articles, all the papers that include the RePlace work. And I also included here an animation. I hope you guys are able to see. And this is how internally the global placement works. Just to give you guys an idea, the instances in green, right? You can see them moving. This is based on electrostatic system. And here it is, an electrostatic system, where, so yeah, the GPL uses this concept, and the idea is that we make a representation of the instances. I'm calling here instances, but you might also call them logic gates, logic cells, there are other names, right? But yeah, the instances, they are represented as positive charges. So this representation uses the density, so how tight the instances are positioned, and the density is represented as an electric potential energy. And if you remember from physics classes, we have this electric quantity, and we make this representation based on the area of the instances. So yeah, since we have charges, we end up with an electric field, and it also results in electric forces, and which generates the movement of the instances. So yeah, the electrostatic system is updated iteratively, aiming towards equilibrium, where in this case we would have no forces, no more electrostatic forces, and no movement anymore when we reach the final of the placement, right? So yeah, GPL is fundamented on a grid of bins. So you can see here on the images, it's the gray squares. So yeah, they divide the core area of the design. The core is like the place where you place the space where you place the instances. All right. So we divide this core area into grids, and we call it a grid of bins. And yeah, the size of the bins will be the average of the size of the movable instances inside of the design. Okay. So yeah, for the GPL grid of bins, a bin inside of GPL will have some important characteristics, such as the density. So the density is a rate of area where we divide the total area of instances inside of the bin. So an example here, the instances in green, we sum their area, and we divide by the actual area of the bin. So how much the bin can actually hold of instances here. So one value divided by the area, it's a rate. While the overflow, it's more of a nominal value. We subtract the area in the bin. Subtract the area of the instances in the bin from the bin area itself. And yeah, we also have the electrostatic forces, which in the two are represented by these red lines here. Okay, so yeah, with the electrostatic forces, it works in a way that denser regions which have more instances clustered together, we should have stronger forces trying to spread them out and yeah, reduce the electrostatic movement. All right, so yeah, we have a minimization function inside of GPL. So we minimize this function here until we reach a 10% overflow. All right, so I also brought here this table on the right. This is the log from the tool itself. If you run GPL, you will see these values here similarly. And it's showing the iteration GPL is going through, the value of the whole overflow in the whole design, the wire length, the change in wire length, and the density penalty, this value here in green. So these are representations of the most important values inside of GPL because of the minimization function, right? So we will have vectors. We call them gradient vectors for each instance, and yeah, this represents each of the instances. So each instance will have a pair of vector gradients, one for the wire length, half perimeter wire length, That's why HPWL, half perimeter wire length, summed here with the density function. Okay. So yeah, we try to minimize them until we reach the 10% overflow. And yeah, we have this density penalty value in green here in the minimization function, which are these values here. So GPL has this cool thing where we try and balance between how much attention we give to wire length versus how much attention we give to density. Because if you think of it, the wire length, if you want to optimize wire length, instances will go tight together, right? They go closer together because this minimizes the wire length, right? If things are closer together, the wire length gets shorter. And since we are on global placement, we don't care about legalization. So if we only care about wire length, we end up with a cluster of all instances on top of each other, which is not feasible, right? So we also have this other portion of the minimization function, which is the density. So we try and reduce the density. So it's kind of a fight between one another. The wire length tries to put things together, and the density tries to spread out, trying to respect the area that the beam can hold, right? And this is done with the density penalty. So in the beginning, we have a small value for the density penalty. If you look close here, it's 10 to the minus 14. And we end the placement with a larger value. And the thing is, we use this value to multiply here by the density function. Since we start with a small value, we give small importance to the density in the beginning, and afterwards we give more importance to the density. And more to the end, we actually spread the instances and respect the beams more. All right, so yeah, as I said, this density balances between the importance we give between wire length and overflow, right? And yeah, I didn't mention this previously, but we have on the project in PII also Lucas Yuki, which is from UFSC. And he recently actually noticed that this equation here from the paper, we use a different one in the code, which is interesting. He noticed that. Not a problem, but yeah, just to mention Lucas here, he noticed this recently. And yeah, if you notice, it's the update on the density penalty will be based on how much we are improving in wire length. All right, so we have these gradient vectors, as I mentioned. So each instance will have two gradient vectors. So since it's a vector, it has a magnitude and a direction. And we sum these two vectors to get a final vector, and this final vector will dictate where the instance wants to move to, right? So yeah, I'm going to talk about each of them with more detail now. So the density gradient, which is the N part here in blue. So in the code, the forces, which I mentioned here, it's the red lines, they belong to the bins, and they are based on a density. That we use the density to calculate the forces, and the forces are passed to the instances from the bins, and it's proportional to the area of the instance that overlaps with the bin. This instance, for example, it overlaps more with the bin on the left, so it will have a higher influence on from the force of the bin on the left. Okay, yeah, so the density function is quite complex, right? As I said, there were multiple papers which worked on RePlace. It was previously ePlace because of electrostatic, right? And yeah, it's quite complex. It has a lot of different mathematical and physical concepts like Lorentz, Coulomb, Gauss, Newman, Poisson. And I won't jump into details. Honestly, I don't understand them in depth, but yeah, we have all of this. And yeah, we also have some differential equations inside of GPL. And with these differential equations, we use a fast Fourier transform, and this is what guides the placement towards equilibrium using the differential equations. All right, so that part was the density, and now for the wire length gradient, it's a lot more simple. We just do a weighted average of the wire length. It's weighted because it's based on the location of the pins. This instance here, for example, it has 4 pins. We have 3 of them to the left, so the vector will be stronger to the left, right? So that's why it's weighted. And yeah, this one is quite simple. Yeah. So yeah, as I said, for each instance, we will sum the two vectors. I brought this example here. This is using the GPL debug mode. If you click on an instance, it will show the internal values of each of the vectors. So we have the wire length part here in orange, their sum. The density vector here in blue, and the sum of them on the end. So in this case here, you see it's a value that's negative on the x-axis and on the y-axis too. So it's pointing to bottom and to the left. I'm sorry, to the left and bottom, right? Okay, yeah. Just to show an example from a single instance here. Yeah, so I wanted to show you guys this here. So this image on the left is the GUI that OpenROAD has. So if you use the tool, you'll be able to see a layout of the design, right? You can see the design here. And recently we included this chart here. So you're not only able to see the values from the log, but you can also see the chart here showing the wire length and the overflow. So I mentioned the density penalty, right? So if you notice, we start with a small wire length. So we start with giving more importance to the wire length. Eventually, you notice how they cross each other. So the density penalty gets smaller, and we give more importance to the density, and as a consequence, the overflow in green starts decreasing, right? And it finishes at 10% here. Okay. Yeah, here I just separated an example of a difference between the paper and the actual implementation of GPL. So in the paper, there is this mentioning that we try to minimize wire length, given that Albin's density is lower than the target density. So the target density is a value given by the user. But in practice, we do not do this. We do not do this checking. We do not check if the beans respect the target. We just walk towards equilibrium and finish when the overflow is 10%. The paper also mentions reaching the electrostatic equilibrium, where we have no forces at all. In practice, this doesn't happen, and we just trust the fast Fourier transform to guide towards equilibrium. But we stop before that, right? All right, so the target density, it's an important value inside of GPL. It's expected that the user will give a target density value, which is universal for all beans. So all beans try to reach this target. It's also used for initialization of the areas, some internal values, and the scaling of the white space for the movable area. We also do some scaling of the beans based on target density. And the target density is different from the actual density that we have in the bean. The actual density is used as an input for the fast Fourier transformations. Okay, so this year I brought an example with 2 different target density values. If you set these values and you run this design, you will get these 2 different results here. This is the end of the placement. So if you notice, with a smaller density, as expected, instances are a lot more spread out, right? And if you give a higher density, you get a tighter placement with instances more tighter together. I hope you guys are able to see, but we have some purple dots on both images. those are the filler instances, as we call them inside of GPL. The fillers, they are used during placement, but they are removed afterwards, and what stays is the instances in green, which are the actual real instances. So yeah, if you use a higher density, you get less movable area, and you get more fillers and a tighter design. Okay, so I also brought these two images here from the paper. They show the importance of the fillers. If you use no fillers at all, you end up with the placement here on the top here, the top right, where the instances, they just spread as much as they can. That's the nature of the electrostatic system, right? It tries to spread things as much as it can to solve the density. So, and we have the one at the bottom, which is using fillers. So the fillers occupy more space and they make sure that the instances are tied together. This happens because the fillers, they do not have any connections. So they do not have an wire length gradient. They only have the density gradient. And yeah, they fully respect the density. And this is how we get a tighter design. Okay, so yeah, these are some images here from the debug mode of GPL. It's a special mode for the developer, and you can see more details in the GUI of what's going on inside of the placement. And yeah, the placement, it usually starts with a high overflow, around 100% or higher. This happens because it usually starts with instances really close together. So we have a lot of instances here. I hope you can see my mouse here. So yeah, all of the instances, they are all tied together here on this small space. So for this reason, we get a high overflow, right? So the beans here are overflowing a lot because there's a lot of area here, a lot more than the beans have able to hold. And yeah, we progress along the algorithm, and you notice how the overflow starts decreasing until it reaches the target of 10%. Okay. So yeah, okay. So yeah, we have this progression of the overflow, and we also have two special modes inside of GPL. So we not only do the placement, we also try to guide it for a routability-driven placement and also a timing-driven placement, right? So we look at some details. I'll try to show you guys what we look into along the placement. So it's not purely the RePlace algorithm, right? So yeah, routability mode first. So we keep track of the overflow that we have. And for the routability mode, it happens between 60% and 30% overflow. So as we progress from the beginning of placement, when we reach 60%, we save a snapshot. So we save the state of the placement as it is when we reach this value, right? And we continue until we reach 30%. When we reach 30%, which is higher than the target of 10%, we run RUDY, which is another academic work that gives an estimation of routing congestion. So routing are the nets, right? The wires that connect instances. It's different thing from the placement, the routing congestion, right? So in placement we have density. The density it's based on instances, but for routing we have the congestion, which is based on wires, right? So two different things. And yeah, so when we reach 30%, we run RUDY, and it gives an estimation of the congestion in the whole design. So GPL looks into this congestion in the design, and it selects the instances which are present in the most congested areas, and it inflates those instances. So it makes the area of the instance a little bit larger. So we make the area of the instance larger than it actually is. With that, we will get more space, right, between the instances, because it's like a virtual area. It's not the real area of the instance. So we pretend, let's say, that it's larger, so we get more space between it, right? Yeah, so we do this inflation based on the Rudy congestion, and we go back to the snapshot. So rotability mode has this kind of limited approach, let's say, that it keeps going back, so it repeats a bunch of times, and it runs between 60 and 30% overflow, right? So we do this repetition with these reverts, as we call, until we reach a target. We have a target routing congestion. So if we don't reach the target, we go back again, inflate more, and yeah, we repeat until we reach the target. The target itself is calculated based on the most congested tiles from Rudy, and yeah, the value currently by default is 1.01. If we reach 30% overflow and we find this congestion value, we stop rotability mode and we just go back to the normal GPL execution to reach the 10% overflow. Right? So yeah, there's a special condition here that it might be that we never are able to reach the target. So for this, the rotability mode, it stores the minimal routing congestion it observed so far. So if we do 3 reverts and we don't find, when we don't get any improvement and we see the congestion is only getting worse, it may happen we inflate so much the instances that the congestion actually gets worse, not better. In this case, we go back to the minimal congestion value that we observed. Yeah, we go back to this inflation value. We inflate the instances with the value that we observed, the minimal routing congestion, and we go back only once, and we progress. We turn off rotability, and we progress normally with the algorithm. It's a little complicated. I hope you guys are able to understand. But yeah, that's just a special stop criteria where we stop if the minimal congestion observed. Okay. So yeah, I separated here two animations. You guys are able to see, right? Yeah. And these 2 animations are for two different designs. And these images, they are only each time we reach 10%. So we progressed on the placement, reached 10% overflow, save an image. Revert, go 30%, save an image again. This is the animation you see here. So each revert, you can see it improves a little bit more the congestion, right? If you look here on this guy here, for example, you see how it starts. On the very beginning, it stops a little bit. Here you see it's a lot darker, the red, so the congestion is larger, right? So with the inflation, it's a little hard to see, but you see the green instances, they spread more. That's because of the inflation. And yeah, in consequence, we get less congestion. By the way, these 2 designs are not even the best examples. I just chose 2 at random, let's say, but there are some which congestion improve quite a lot, and yeah, it works well afterwards because we are during placement, right? But afterwards, during routing itself, results do get better with this approach here. So yeah, this is the rotability special mode for GPL during placement, and we also have the timing-driven special mode. So the timing driven is a little more simple to understand. If you notice, I inserted here some overflow values in red, and this is when we run timing driven. When we reach 79% overflow, we stop the placement, let's say, and we call the resizer RSZ. It's another tool in OpenROAD, so the 2 tools are integrated together. And yeah, the resizer, it uses OpenSTA, which is yet another tool, and calculates the slacks and timing related aspects of instances. And with that, we are able to detect the instances that belong to the worst paths, as we call them. So the worst paths are like the paths between wires of a path will be multiple wires that connect multiple instances, right? And there is a time for the signal to pass between those instances and wires. And the worst paths are the one that takes longer, right? If it's negative, it's violating, so it's incorrect. It's taking more time than it should to reach the final instance, let's say. So yeah, we have these slacks that the resizer calculates, and with these worst paths, the instances that belong to these worst paths, we give them timing-driven weights, as we call them here in this arrow. So for these instances in the worst paths, we give more importance to the wire length portion. This is just an attempt to keep instances in the worst paths closer together, right? So yeah, this is done multiple times, 5 times in the flow, in the GPL execution. You also see this non-virtual name here. This is a contribution of mine because previously the GPL and resizer were not properly integrated, and today they are integrated. That's something I was able to help with. And yeah, the resizer not only calculates the slacks, as I mentioned, it also does buffer insertion and instances resizing, which are two methods to improve timing. So previously, we did virtual iterations where the resizer does its work, but it doesn't stay in GPL. GPL was not aware of it. So today it's non-virtual, the work where the resizer stays in GPL with the new buffers and also the weights for the wire length gradient. So yeah, previously we had 5 iterations for the timing driven. We noticed that the resizer is costly in runtime, so we recently reduced this to only 2. We do only 1 timing driven iteration before rotability and 1 timing driven iteration after rotability mode. And this improved the runtime, and we didn't see too much difference in quality of results. Yeah, also this is another change I made recently to the GPL2 in the debug mode. It's now coloring the instances based on based on how the instances were modified. I'm sorry. So in white, you will see the instances which were inflated by rotability, and in blue, the instances which were modified by the resizer. Yeah. Okay. So this slide here, I brought two examples, 2 design examples here. And in the right, you see some plots with the overflow in blue and the wire length in orange. Also the density penalties here. So you see these vertical lines, you see the ones in red are for the rotability mode. So you see how we progress and go back, because of the reverts that I mentioned, right? And yeah, we also have the 2 timing driven iterations in the beginning and 3 in the end here. Yeah, just to show you guys an example of how the placement works overall. You see how, and this guy here, for example, it goes back a lot of times. This is the rotability mode working. While this one, it has a lot less congestion, so rotability runs less times. All right, so a limitation for GPL is the divergences. Sometimes they happen. We are unable to find a solution to the placement. We have 2 types. One is a division by 0 or infinity also. This one usually happens when a user makes something wrong. But we also have this other divergence here which is a limitation of the tool itself. Unfortunately, it happens sometimes when we are not able to the fast Fourier transform. It doesn't guide anymore towards equilibrium. Something goes wrong in the calculations, and we are not able to reach the 10% overflow. So last year, working on OpenROAD and GPL, we would constantly get reports by users complaining about the divergences. So I couldn't figure out a way to solve these divergences, but I could come up with this was the solution, workaround, let's say, where we keep a snapshot of the best solution we have so far, and we are able to detect if a divergence is happening. And if detect it's happening, we go back to the best solution we get, and we finish the global placement with this solution, an incomplete one, right? Because it didn't reach the target of 10% overflow. But yeah, users are happy with this, I believe. I do not see issues being created anymore because of the divergences. Yeah, here are some contributions that I made to GPL, some of them. So today, GPL, the implementation in C++ itself is able to remove and insert instances in the middle of the placement while it happens. This was quite challenging to implement because GPL is fundamented with vectors, C++ vectors. So if you know vectors, they are static. They are not made to be changed. So yeah, then it has parallel vectors. It's really messy, let's say, but it's messy for a reason because it's really good in runtime. So yeah, it was quite a challenge to make this enable the tool to insert and remove instances during execution with parallel vectors. So yeah, recently we also are able to remove fillers. This is not an open PR anymore. It's finished. Yeah, challenges. Yeah, this is not really important for you guys. Yeah, the parallel vectors that I mentioned already. Some further challenges. Yeah, so GPL not recently, some years ago, we introduced multi-threading to GPL, but it's not good. I noticed that if we increase the number of threads, we get no improvement in runtime, and we use resources a lot more. So this is a limitation. So yeah, can we make divergences never happen? It's an open question still. Yeah, runtime bottlenecks, the time driven is really costly. And routability mode sometimes do a lot of reverts with very little improvement. Just to mention some limitations. Yeah, this slide here, I did thinking of you guys, the listeners in the class. So some suggestions here, some links for people if they wanna get started with OpenROAD. You see the documentations online. So there's documentation for installing the tool. Once you have it installed, it's really easy to run, super easy. You just type make, and it should run the simplest design that we have. We call it GCD. So let me just open it here for you guys to see. So you have this documentation. So you see here what you should do to install the tool. You do git clone and sudo setup. This is new to me, but I believe this already installs all dependencies and installs the tool itself. So yeah, really practical. Back then, 5-6 years ago, when I started working with the tool, it was not easy like this. Yeah, there's a lot of things here on the guide. There's a tutorial here. So there's this flow tutorial. Maybe it's this one. Yeah, this one, flow tutorial. So you see, there's a lot of things here, a lot of different things you can do with the tool. I don't know how to open a design here after it ended, changing the design you want to run. Yeah, viewing the layout here. This is the appearance that the tool has with the GUI. Connectivity, clock tree, it's quite complete. You see here the clock tree and the paths. Yeah, the clock tree viewer here, it's important for the clock. Heat maps, we have placement heat map. This is outdated here. There's more heat maps today. We have density, power, the heat map, room congestion heat map. Today we also have Rudy, IR drop, a lot of things, timing report. So yeah, it's quite complete too. And you see here the documentation of a simple tutorial how to get started with things. This first link, as I said, you can just use make. Oops, you just use make and that's it. You should run. Just some suggestions here of what to do if you want to get started with the tool. And I wanted to emphasize here, if any of you guys happens to want to do some project in EDA, as I did back then before my PhD, it's the OpenROAD. I incentive you guys a lot to try it out. It's free, it's open source. The community is extremely active. You feel free to ask questions if you happen to use it. Back then, when I started with the tool, I used to make a lot of questions in the GitHub, and it always got answered. So yeah, it's a really active community. I even had the opportunity to make a suggestion there. So you see these heat maps we have. I wanted for my project for the PhD to have these heat maps in CSV format. So the tool didn't provide that. And I'll make a question there. Oh, how can I do this? How can I get the heat map values in CSV, not just the image, right? And like 1 week afterwards, oh, here's a command that new command that you can do it, right? So yeah, really active community. And there's a discussion tab for OpenROAD and for OpenROAD flow scripts. People make questions. You can even see here, quite active, 2 answers, 3 answers. People make all sorts of questions, suggestions. So you can come here and make a question, no problem. And yeah, there's also this, recently I noticed this new label here on the discussions. Good first issue. So if you want to find out an idea, I don't know, maybe there's something here that you might find interesting to do and change on the tool. Personally, my first addition to the tool was that I know something really simple. I noticed that when the tool finished after detail routing, it gave all the runtimes of each step, but it didn't give the total runtime, right? So I noticed this detail, and yeah, I suggested the edit. You created PR for this. We call it pull request, and it got accepted, and I made my first addition to the tool, contribution to the tool. So yeah, really cool. I don't know, maybe if you're interested, you can do this too. Right. And finally, this link here, I noticed this recently. This is for my company, the Precision Innovations. So it has a lot of videos here, a bunch of videos with a lot of things for you guys to watch. These 2 first ones are more general videos for talking about OpenROAD. So yeah, you have the installation, the flow structure, a lot of things, how to configure things here, automated RTL to GDS flow, how to configure setup using the make command, as I mentioned, logs, reviewing the logs. This is important after you are able to run a design. You want to see what happened, right? So we have the logs, we have the reports, final checks, the GUI, what you can do in the GUI, heat maps, macro placement. Yeah, a lot of videos here. If you are interested, I hope you guys are. I think it was really constructive for me to work on the OpenROAD project because I worked with it during my PhD, and afterwards I got hired, and it will be my second year at PII in December this year. So yeah, that's it, guys. I hope you guys were able to understand something about GPL, about RePlace, and I hope I'm able to incentivize you guys to actually use the OpenROAD tool, and I'm open to questions.
Okay, thank you, Augusto, for the quite detailed presentation. Do you have any? I don't know if I will be able to. If I should. No, I should change the camera. I'm losing the. Okay. Okay. Do you have questions? People from the audience, do you have questions?
Is there a lot of people contributing now on GitHub, like since it's open source?
Yeah, good question. Yes, we do. So we have all the PII developers, right? We are a team. The team is growing currently. It's actually now that you asked, they are actually hiring currently. So yeah, we have a team of, I don't know, maybe like more than 10 people, certainly 15 people currently. When I started, it was less than 10 maybe. And we have all of the users, right? So we have our clients from PII. They actually don't talk to us. They talk, we discuss on the GitHub itself. So clients from PII, they make issues and discussions in GitHub. So we have all of the clients from PII talking and contributing there. And yeah, it's quite active. A lot of contributors. Yeah, definitely.
Yeah, but the people that has been has a contract, working contract with Precision Innovations. How many are working these days?
Yeah, as I said, I think it's about 15 people.
15 only. I thought it was more than 20.
No.
Okay,
Yeah.
because from UFSC, there are these days. I think there are 4 students.
Yeah, let me see. It's Lucas, João Mai, Arthur J, as we call him, João Lourenço, me. Not me. I'm not from UFSC anymore, I guess.
I'm not counting on you. Yeah, but okay.
Yeah, it's those.
Oh,
there are people from URGS also. Yeah.
Okay. Yeah, two former students from the Federal University of Rio Grande do Sul. Actually, Eder was the first Brazilian working for OpenROAD with a contract, as far as I remember. Then now there is also Arthur Culture, right?
Yeah, Arthur K is from URGS, yes.
Okay, and it seems that there is a new student from Porto Alegre also working now.
Two of them. We have Jonas and Rafael, both from.
So there are 4 from Porto Alegre and 4 from.
Yeah, at least. Yeah.
Okay.
At least. So, by the way, it's important to mention, Ginzel. So, our boss, my manager is actually looking for Brazilians. They want to hire Brazilians. So they are interested in Brazilians.
Must be Brazilians.
I don't think it must be, but if it is, it's a plus. Yeah.
Can be Norwegians.
Probably, I think so. Probably.
Okay, I have some questions. I would like just to pose some of them, because after we could actually talk a little bit after the presentation. But my first question would be concerning the objective function. I don't know if you could put in the slide showing the objective function, like this one, for instance. So in this function, are you considering the summation of all wire length and congestions at the same time? How are you dealing with? So actually, I think I didn't understand what is the V in this equation. Okay, so V is the set of all all standard cells, for instance.
Yeah. Okay. So this is a representation of all the instances. We have a pair of vectors for each instance. So this minimization function is representing all of the vectors, right? So.
Oh, I see. The V stands for vector. Is that?
I think so. I believe so. Yeah.
Okay. So, but this equation comes directly from the RePlace paper. Let's say
Yes.
the original RePlace paper.
Mhm.
Okay, and the lambda factor there, is it? I may have lost something, missed something in your presentation, but is lambda fixed value, or it evolves during the? Oh, I see. Yeah, it evolves during the progress of the algorithm, the solution, right?
Yeah, you can see the values here on the right.
Okay.
It starts with small value and a less smaller value. Yeah.
Okay, but then is it possible for the user, I mean the designer, to influence on the value of this lambda, on
Yes,
how
he
this
can.
lambda evolves?
He can. I'm showing you here the README. So this is the README for GPL only. So if you go on OpenROAD source GPL, you see the README. Each tool has its own README. And yeah, you notice how it has a lot of parameters. You can change them. Yes, some of them here are for the panel. Yeah, you can change the initial value. And
Okay.
that's it, I think. No, these phi values here are also influence the density penalty.
Okay.
Yeah.
Okay, that's right. But concerning the wire length, I don't know if you could please move to the slide when you're showing the example with I think it was BPE something example. Yeah, this one. Yeah, exactly this one. Okay, so how are the macros terminals dealt during the solution, during the RePlace evolution?
Okay. Yeah. So the macros, they are fixed. They are placed by the previous two, by MPL.
Okay.
And yeah, MPL does the placement of the macros, and they are set as fixed. And afterwards, GPL comes and only moves the instances.
Yeah, but I was referring to the. Actually, I was referring to how if the terminals, the input and output pins, for instance, normally there are a number of connections between the macros and the cells that are being placed. So how, for instance, in the W factor of the equation, is the wire, is the length of the wires connecting the input and output pins of the macros to the cells that are being placed? Are they considered also in the
Yes, definitely. Yes. But I mean, it's a connection between two pins, right? So one of them will be fixed. That's it. The other one is movable, right?
Yeah, one would be the cell that is receiving or sending the signal and is being moved and is being placed, and the others are the fixed pins in the fixed macros, the already placed macros, right? Yeah.
Yeah.
Yeah, I was wondering because if the algorithm spreads the cells that are being placed, the connections between those cells and the macros are going to be shorter, right? So if you work to reduce congestion by spreading the cells, you are going to increase the average wire length between the cells, but you're going to shorten the connections between those cells and the macros. So how are those two metrics dealt during the evolution of RePlace, during the process of RePlace? Because it seems that there is no many changes in total wire length, right? Oh, actually, there are, because the wire length tends to become worse while you are spreading the cells, right?
Yes, it does. Yes.
Yeah, but then it seems that the lambda factor must be increased very fast. Otherwise, you're not going to get a good solution by spreading the cells, right?
I'm not sure I follow your question, Ginsu.
Yeah. Okay, so the point is that in the very beginning, you have all cells concentrated in the, say, central region or a given region of the placeable area of the circuit. If all cells are placed in a very small area because they are overlapping themselves, the total wire length will be very, very short. Okay?
Yes.
But this is not a valid solution because you really need to spread the cells so as to reduce congestion. But then by spreading the cells, you are going to get much longer total wire length.
Yeah, definitely. Yeah, so that's the minimization function, right?
In the very beginning, you don't the algorithm possibly won't be able to give a lot attention to the wire length. I think that it doesn't make sense to give much attention to the wire length, and the wire length would be something more important just in the end of the progress.
It's actually the opposite. we start with more importance to the wire length. I understand that in the beginning it finds the clusters of instances, so it ends up along the progression. Since it starts with importance to wire length, they tend to cluster together the instances which are heavily connected, and as we start to give more importance to density, the clusters kind of keep together as they are, and but we do spread them respecting the density. That's why you sometimes see clusters here, right, of instances. But yeah, that's how it works. The two objectives. Sorry.
Yeah.
The two objectives are they fight between each other, right? They are opposed to one another. So
another question is concerning the inflation procedure. The inflation procedure, does it work only in the region that must be inflated? I mean, there's no when it is applied, the current solution from the electrostatic model is fixed, and only the region that must be inflated is treated. Is that?
Yeah. In this case here, we would not get any inflation on instances on the green regions, right?
There's no newer solution, no newer call of the Nesterov solver. So I'm talking about Nesterov. If you know that the core solution of the electrostatic model uses the Nesterov solution, right? So it's
yes, I didn't mention it.
That you didn't touch this because it's really hard. But so there's no new. Let's say, okay. Actually, when inflation begins, or after inflation, after congestional air optimization, you have also the timing-driven optimization. For those two steps, no new Nesterov solution is generated, right?
You mean something like a solution in parallel? No.
No, I mean calling again the solver, the electrostatic solver.
It's the main thing. The Nesterov is always present here, actually. So my representation of this arrow of the overflow, this is actually the Nesterov.
Nesterov, okay. So Nesterov is going to be called again.
Yes. In a sense, yes. It never stops acting. Actually, it's always there.
Okay. So
we just change the area. That's it. We just changed the area, and Nesterov does all of the work.
Okay, so the rest of the circuit is kept as it is, and Nesterov is solved again only in the target area. Is that?
Yes, we just changed the area.
I see. Okay.
Yeah.
Good. Okay.
Nesterov is the main guy here. I didn't mention him, but yeah,
Okay.
it predicts the next step, right? It's
Okay, right. Okay. Yeah, and a final question is that I was quite surprised that buffer insertion and also gate sizing is done before detailed placement, right?
Yeah.
So normally, in my mind, I thought that buffer insertion would take place only after global placement, after or during, as an extra step after detailed placement. So you're showing that no, it's actually both steps are applied still during global placement. So how are the solutions? How are those buffers insertion solutions treated after that? I mean, is there a new step? I don't know if you know this, because this is going to be the detailed placement. So for the detailed placement, are there any new steps of time optimization by buffer insertion or gate resizing?
Sure, Ginsu. So this is really important along the whole flow, right? Not only during global placement. In practice, we call the resizer, this tool here, it's called multiple times along the flow. So it's called like after the logic synthesis, before and after, and I think even during for planning, before and after global placement. So it's also called during routing. So during, before, and after routing, we also call the resizer, and it also has different commands, different approaches to do different methodologies for improving timing, right? Including buffer insertion. For GPL here in this, for instance, what we do here is that we currently remove all buffers and insert them again during the placement.
Yeah.
During global placement. That's what we do now.
Just like the feeder cells. The feeder cells are used just to allow a better spread of the cells, and then after that they might be.
No, yeah, they are removed, but they are kept after global placement. They are kept.
They are kept.
Yeah, we just remove all. I mean, when this iteration starts, it first removes all the buffers, all the existing ones, reinserts them, and then continues the flow. Yeah, and it will be true also for other steps. Yeah.
Okay. Any other question? I was just taking almost all questions. Do you have any other question? Not exactly technical ones, but. Okay, I have just one comment, very curious comment, because today, this morning, I received an automatic notification from Google Scholar about a paper that has been made available in the archive, which is exactly on electrostatic placement, and they say that they are improving the runtime of electrostatic by using a fast Fourier transforms solver. Okay, so I'm going to send you this paper right now.
Okay.
The reference. I was so curious, because I was just today receiving this notification today, exactly today, that you are going to make your presentation. So it's quite
There's
coincidence. Okay. So let's thank Augusto with a warm round of applause. Thank you very much, and it would be very nice if you could send me the PDF of your presentation so I can
Sure.
make available for the students in the Moodle page, okay? Okay, thank you very much. And
Thank you,
bye-bye.
Bye-bye.